Okay, here are two circuits. Here's your chance to practice and get ready for the final exam. You know the routine. First we'll close the switch across here and you'll have an LR circuit, and you know how that behaves. And then after that reaches its final stable state, we'll close the switch to the lower position and we'll have an LC circuit, and you know how that behaves. And you should do that for both circuits, the top one and the bottom one. And just for practice, do graphs of the voltage and current through all circuit elements. Voltage and current. So that could be up to 6 graphs. Some of them obviously are going to be simple. And additionally, write the equation with numbers. The graphs should have labels, units, numbers, and the equation should have labels, units, numbers, the equation that match each one of those graphs. Okay, that's a lot of writing. You maybe don't need to write it all out, but you should be able to do that. So that's, in principle, 6 equations and 6 graphs when we close here, 6 equations and 6 graphs when we close here, and then the same for the bottom circuit. So do as much of that as you can, and when you get stuck, come back and I'll help you through it. Okay, so you're back. This is the plan. I'm going to close the switch here and do this LR circuit. That'll be 6 graphs and 6 equations. And then I'll close the switch here and do this RC circuit, 6 graphs and 6 equations. And I'm going to do it quickly as a review, because you can pause and reverse the video and just check this against what you did. So you really should have done most of what I'm talking about already, if you possibly can. And if you're having trouble with this circuit, remember there's a longer, slower video about LR circuits, and you might go back and take a look at that if you don't know how to handle the LR circuit. Okay, so pause again if you think you can do more, and then come back and I'll show you what I'm going to do. Okay, back again. So the first thing to notice is that in this circuit, when I close the switch, I have a closed single series loop, and the capacitor is completely out of it. So the voltage across the capacitor and the charge on the capacitor will remain 0. Similarly, when I close this switch, I have a series circuit with a capacitor and a resistor, an RC circuit, and the inductor is dangling and not in the circuit, and the current and voltage across the inductor will remain 0 the whole time. Okay, so that's first item. Second, on this circuit, when I close the switch, normally you close a switch, you get a current, but since the inductor is there, it's going to stop the current. So you remember the rule that current through an inductor can't change instantaneously, so when the switch closes, the current is 0, the current will go from 0 and it'll rise. I'll show you this graph later. It's going to rise exponentially to its final value, and you can see that the final value is going to be the voltage divided by the resistance, so 8 divided by 20, which would be 4/10 of an amp. Since the current is 0, the current through the resistor will start at 0, and the voltage across the resistor will be 0. And the entire 12 volts at the beginning, the entire 8 volts at the beginning will be across the inductor. Why? Because the inductor doesn't like it or reacts when you try to put current through it. So it responds with a reverse voltage of 8 volts to try and slow down the current. Okay, now I'm going to show you the graphs and the equations for what I just said. So to do that, let me I'm going to why don't you pause the video? I'm going to pause the video so I can write all that out and not waste your time having you watch me write. Okay, here are the 3 graphs. I'm going to show you 3 graphs and 3 equations. Remembering, notice that I shrunk the circuit to get it out of the way. And I'm going to, and the capacitor I'm not doing because it's 0 the whole time. So what I said was the current on the inductor has to start at 0 because currents can't change instantaneously, and it's going to rise to 4 amps exponentially. And so notice how I graph this. I go to the first time constant and I go 2/3 of the way and I put a point. Then I go to the next time constant and I go 2/3 of the remaining way and I put a point, and I'm going to run into this equation, but don't mind that. And I go a little bit higher, and then when I draw the line I can use these points. And what I often like to do is show this 0.4 volt with a dotted line. So that's the current, and notice that there is only one current. The current through the resistor and the inductor is going to be the same. So if you're asked to plot the current through the inductor or the current through the resistor, it's going to be that current. Now the voltages are opposite. So let's put in our asymptote line for 8 volts, and one of them, that's the voltage across the resistor. Remember why? The voltage across the resistor starts at 0 because the current starts at 0, and the voltage across the resistor has to follow the current. So the voltage across the resistor is going to do the same thing, 2/3, 2/3 more, 2/3 more. It's hard to do here quite exactly, but something like that. And notice I put in the time constant for the circuit, the L over the R, 1.5 milliseconds, so you should have that, and I put it in here. And if it weren't for the space problem, I would have written it in here as well. I noticed I left one important thing out, and that's labeling this axis time in milliseconds. So make sure you have that label. Okay, so we showed this. This graph is our VR, and of course the VC, the VL, the voltage across the inductor, does the opposite thing. It starts at 8 volts because in the beginning, remember, the voltage across the inductor depends on the di dt. So this starts high and decays exponentially towards 0. And notice that the sum of these two voltages at any point will add to 8 volts. Actually, what I should have done was put that on the negative axis. So if I had, let me just show you with the pointer. If I had graphed it here, starting at negative 8 volts and going this way, then the sum of the two voltages at any point would be wait a minute, let me pause the video. Okay, so sorry about that unclear last minute. What we know, let's remember what we know. We know that the voltages around a closed loop, I'm referring to this little circuit which you can't see so well, have to add to 0. And so the voltage on the resistor and inductor have to always add up to a negative 8 volts. Now I plotted them on the positive side. Strictly speaking, they might have been plotted on the negative side, but just think of it as the absolute value of the voltage. So at any point, here it's 0 and 8, here these two numbers would add to 8, and at any point, if we add those two voltages, they add to 8. So that will be equal and opposite to the 8 volts on the battery, meaning that the sum of the voltages around the loop are 0. That's Kirchhoff's law. All right, lastly, notice the equations that go with these graphs. So you know that a charging exponential is 1 minus e to the t over the time constant. We got the time constant. And it goes, the value of the quantity, current or voltage, will go either from a maximum value to 0 or from 0 to a maximum value. And that's what this does. So this equation describes this behavior. And this equation describes the behavior of the VL, decaying exponential. And if I were to write the equation, which I didn't do because of space, for VC, it would have the same, for VR, the voltage across the resistor, this one, the one that charges, right, because the current rises, so the voltage across the resistor rises. And that would follow this equation, only I would have V here, I would have V max, or the 8 volts here, and it would look like this equation, only it would be 1 minus e to the minus t over the time constant, 1.5 milliseconds. So I hope that checks out with all your work. Now I'm going to go back and do the capacitor circuit. Okay, here's the capacitor circuit. Now to save time, I'm going to go over this even faster. So what do we know? We know that when we close that switch on the capacitor circuit, the inductor's not in the circuit, so that stays at 0, and the capacitor begins to charge. But since it's empty when we start, it has to start at 0, and it has to charge exponentially to a final value. Now, since the capacitor starts with 0 charge, it has to start at 0 volts. And since it's empty, it means that the current starts high. Opposite of the last one, the current will start high and decay, because when the capacitor charges, it will stop the flow of current, and so the current goes to 0. And similarly, since the capacitor is charging, the voltage across the capacitor is rising, and since the current through the resistor is decaying, the voltage through the resistor will also decay. And so what you should have is the time constant marked here, the t in milliseconds. We need to calculate what this maximum charge is. We know the maximum current is 0.4 amps. It'll be the same because we have the same resistor and battery. And we know that the maximum voltage is 8 volts. So the voltage across the capacitor will rise to 8 volts. And the voltage across the resistor will start at 8 volts and decay to 0 volts. So when the capacitor gets to 8, the resistor is at 0. When the capacitor starts at 0, the resistor is 8. And that, once again, is Kirchhoff's law, because the battery is 8, and so the opposing voltage, or the sum of the voltages around the loop, has to be 0. And the equations, you can refer to those equations. So an equation like this, I'll write just the one, would be Q equals Q max, which we haven't figured out. I'll do that. 1 minus e to the minus t over the time constant, oh yes, RC, ran out of space. Let me pause the video and do both those calculations for you in case you want to check your answer. Okay, so just finishing this up, the Q max, we use the equation C equals Q over V, and we solve it for Q, so Q equals C times V. The Q max is going to be the C times the V max. So that's the 40 microfarads times the 8 volts, or 320 microcoulombs. And the time constant for an RC circuit is just RC. So that's the 40. Whoops, I multiplied that wrong. That's the 40, yeah, that's right. The R is 20 and the capacitor is 40. So it's 800 milliseconds or 0.8 seconds. Okay, now we're going to throw the switch down and see what happens with the two LC circuits that we have. Okay, so here's the two circuits. We're going to, the switch is closed. In this case, the inductor is charged with 4 amps, 0.4 amps of current. And we're going to close the switch down here. And what's going to happen, we're going to have, what you should know is that this is an oscillating circuit. The LC circuit is an oscillating circuit where the current, the voltages and the energies oscillate back and forth. The capacitor charges and uncharges, the inductor charges and uncharges, and the functions are all sines and cosines. So we need to do that. And over here, we reached a point where the capacitor's charged, and so when I close the switch down here, the capacitor is going to discharge and charge the inductor with current. The current in the inductor is going to charge the capacitor in the opposite sense. The current will stop, the capacitor will come back, charge the inductor in the opposite sense from what it was last time. And so the capacitor will charge the inductor will charge the capacitor, and the current in the circuit as the capacitor charges and discharges will oscillate back and forth. Everything oscillates according to a sine or cosine function, and those forms are on your equation sheet. So pause the video and see if you can do those equations for the inductor and the capacitor on both circuits. And notice you can plot the current through the inductor or the charge on the capacitor. You could plot the voltage across the inductor and the voltage across the capacitor. So you could do 4 graphs for each circuit. That would be 8 graphs. Oh my gosh, we're already 17.5 minutes into this. Okay, so I'm going to pause the video. You are too. And you're going to do as many of those graphs and as many of those 8 equations as you possibly can. Refer to your equation sheet. Okay, let's do the first 4 of the 8 graphs. We'll start with the inductor, the upper circuit where the inductor is charged. So just quickly, the inductor has 0.4 amps going through it, so that's where we start. The 0.4 amps is going to charge the capacitor. It's going to go to 0. The capacitor is going to charge the inductor in the opposite direction as it discharges. The inductor going in the opposite direction will charge the capacitor in the opposite direction, and that will recharge the inductor back to the original current. So you can see it's a cosine function. Let me trace that in for you. So we start high at 0.4 amps, we go through 0, we go low to a negative 0.4 amps, we go back through 0, and then it recharges the inductor with 0.4 amps. So the energy, so that's a cosine function following the form on your equation sheet. Now in order to plot this, we needed to know the max and the min, and I know in this case, since the current started at 0.4 amps, it's going to oscillate back and forth between 0.4 amps. So I had to find the period, so I used the period equation to calculate that. The square root of LC is this number, times 2 pi gives us this number. So 218 milliseconds is the period. That means this cycle repeats every 218 milliseconds, or 0.218 seconds. I didn't put that in everywhere, but you can see I put it in down here. So this would be 54.5, 109, 1, whatever that is, 60, 5 or something, and then 218. And so we have the current, because that's the thing we know. Now, we know the capacitor starts uncharged. How do we know that? Because it was uncharged, right? It can't instantaneously charge. So we know what the current is, 0.4 amps. We know the capacitor starts uncharged. So the capacitor is going to start at 0, and it's going to charge to its maximum value, which we have to calculate. We already know the period. All of these things are going to have the same period. We calculated that here. So the equation, so to get what is the capacitor going to charge to? Now don't make the mistake of using the 8 volts. That's gone. What the capacitor is going to charge to, it's going to charge to whatever charge is the energy stored on the inductor. So this is an energy equation. The energy stored in the inductor when we start will be all transferred to the capacitor when it reaches its maximum value. And so if we set these two energy equations, this is the energy on the inductor when it's at its maximum value, and this is the energy on the capacitor when it's at its maximum value. And that solves out to be this, that Imax will be Qmax over LC. And so to get the Qmax, I'm actually rearranging this equation so that it reads Qmax, that's what I want, equals Imax, that's the 0.4 amps, times the LC, and that's the 34.6 milliseconds. So I didn't write that down. Let me pause the video and calculate that. So once again, I took this equation and rewrote it to get Qmax, knowing that this is 0.4 and that this is 34.6. We calculated that up here. And what I got was that Qmax is about 13.9 milli. So that would go here, 13.9, and the units would be millicoulombs. And of course, the charge, as we mentioned, starts at 0. It charges to this maximum value, so it's going to go like this. Then it's going to go back to 0. It's going to recharge to the same maximum value in a negative sense. And so this would be represented by a sine function using the standard formatting that you'll see in on your equation sheet. I don't have time to write that down. Let's go through the other two equations and then we can discuss that. So remember, the voltage on a capacitor is directly a function of the charge on the capacitor. So the voltage on the capacitor is going to follow the same thing, only, oh, well, what is the voltage going to be? So don't make the mistake of saying that the voltage is 8 volts. The 8-volt battery is gone. And we're going to use this equation. So we got the Qmax. And so we could use the equation to get the VC. We could use the equation that the voltage on a capacitor is equal to the charge on the capacitor divided by the capacitance. So that's the equation you would use, and you would come up with the value that the voltage is 0.3464. So that's what it's going to charge to. Let me write that in. 0.346. And if we, again, it follows, so it's going to look like this, and it's also a sine function, same period, just a different maximum value. And now the voltage on the inductor, remember it's not related to the current, it's related to the change in current. And to get the voltage on the inductor, we use Kirchhoff's law, as we often do. It has to be equal and opposite to the voltage on the capacitor, since in this circuit there's only those two elements. And so if the voltage on the capacitor is a sine, the voltage across the inductor is going to be a negative sign. And it would look like this. And it would go back and forth to the same two values, the 0.346 volts. So there you have it, everything but the equations. Let me write out the equations for you. Pause the video and see if you can write out. I'll write out one or two of them. Okay, here's the two equations that go with the first two graphs, and if you get this, you certainly can do the rest of it. So the I is the cosine function, and so the general format is I equals I max cosine of 2 pi t times t, where the 2 pi t is 2 pi divided by the period, and 2 pi over t is also called omega, the angular frequency. And if I calculate that out for this problem, these are the numbers I get. I get I equals I max, that's the 0.4 amps, we know that, times the cosine of this number, calculates out, it has units of radians per second, or 1 over seconds. And this will give us an angle in radians. So it's 28.9 1 over seconds times t. And every other function is going to either be a sine or a cosine with the same period. So we saw that the charge started at 0 and went to this maximum value, so this is a sine function. So Q on the capacitor is the 13.9 millicoulombs times the sine of the same 2 pi t over t times t. And that covers that. We'll go on to the last circuit now. Okay, just quickly, this is the circuit. This is the last remaining piece. We've closed the switch here, we've charged the capacitor, now we're going to close the switch here, and the capacitor is going to discharge in this oscillating LC circuit. So see if you can do the 4 graphs and the 4 equations for this, and then check back. Okay, we're about to finish. So we're back to that second circuit. And it's a little hard to see, but we calculated the values for that. Where are they? They're down. Well, they're a little too small to see. I didn't write it in. But anyway, if you go back there, you'll see that we had that the maximum value when the capacitor was charged was 320 microcoulombs. I think I can show you that just quickly. So we have in this circuit, we're charging a 40 millifarad capacitor with 8 volts. So if we do the 1/2, if we do the Q equals CV, we have 8 times 40, which is 320. So the capacitor starts charged, and it's going to discharge, putting current, let's draw that. It's going to discharge, putting current through the inductor. The inductor is going to charge the capacitor to 320 microcoulombs in the opposite sense. It's going to go back to 0, and then it'll recharge it in the positive sense. And so the charge on the capacitor is going to oscillate according to a cosine function. Since the capacitor starts charged, it's at full voltage. And in this case, it was charged by the 8-volt battery. So the voltage across the capacitor has to be 8 volts. And it's going to follow the charge on the capacitor, because that's what determines the voltage. So it's going to oscillate also as a cosine function, varying between plus and minus 8 volts. The voltage across the inductor has to oppose that. The sum of Kirchhoff's law, sum of the voltages have to be 0. So that has to start at a -8, go to 0 when this is 0, go to a +8 when that's -8, and so on. It's going to be a negative cosine function, all with the same period. And notice that the period is the same as it was in the last circuit because we have the same L and we have the same C. And you remember that that equation for the period is the square root of LC times 2 pi. All right, so the last thing is the current. So the capacitor starts charged and it puts current through the inductor, but the inductor started with no current in it. So that's where it has to start. It has to start at 0 because that's what it was. And the capacitor acts like a battery, pushing current through the inductor. And since the current is di dt, we start with 0, right? The derivative of the I is dq dt, and so the current is the derivative of this. So here the current is 0, the current when the slope goes negative, so the current has to go from 0 to its negative maximum value, back to 0 to its positive value, and then back to 0 again. So it's a negative sine function. And that's the last thing we have to find out. What does the current go to? Okay, well, don't think that it's going to be the same as it was in the earlier circuit, because this is a different circuit. And so we have to use our energy equations to find the current, and those are buried in this graph here. And it's that I max equals Q max over the square root of LC. And if I use that, what I come up with, surprisingly enough, is 9.24 amps plus or minus. So let me write that in, if I can squeeze it in. 9.24, that's what you should have gotten, and that's, so there's a lot more energy in this circuit in terms of current and charge on the capacitor than there was in the last circuit. And the last step, I'll just do it quickly, is write these equations. You should be able to do that, but I'll do 2 of them for you. All right, finishing up, here's the first 2 graphs. There's Q on the capacitor equals Q max cosine 2 pi over T or omega T. And the numbers are 320 millicoulombs is Q max, and that was the 2 pi T over T, or the omega times T. And for the current, it was a negative sign, so I put a negative sign in there. That's the maximum current, and that's the frequency at which it oscillates, or 2 pi over the period at which it oscillates. And the rest of the equations you could figure out from that. All right, I think we're done. Goodbye.